Hello guys, this video is focused only on implementation, how to program VHDL for a particular project. It's not intended to teach you syntax, how to use tools or anything else. Servo motor rotation control via angle. For our implementation, we will denote angle as position value. Therefore, when position value is 0, angle 0 degree is achieved. When position value is 512, the servo motor rotates to 150 degree and so forth. Let's see how this position value is realized in FPGA. As shown in the picture, position 10 has smaller time on value, whereas position 100 has longer time on value. Let's see how this calculation is achieved for the FPGA implementation. We're going to implement only position range from 0 to 55. This is just an example. Please use it as you would like to. So in the FPGA, 0 to 255 position is mapped to 50,000 to 150,000 counter value. That implies when a counter counting from 1 reaches to 50,000, it means that position 0 PWM could be generated. Whereas when it reaches to 150,000, position 255 PWM will be generated. I have taken a hardware which is running on 50 Hz. Therefore, the time period of the clock is 20 nanoseconds. Hence, if we have a clock sync counter count from 1 to 50,000, then 1 millisecond of time period will be passed. This position, if it's added to 195 and the mapping range is divided by 256, then the value will be equivalent. Therefore, at this position, we will toggle the output pulse. Let's see how this output pulse is controlled. For understanding, I have named the output pulse as PWM output. The position request is 10. Counter start from 0. At this instant, PWM output is set to 1. When a counter reaches 10 plus 195 multiplied by 256 value, then the PWM output is set to 0. And again, counter continue to count, and when it reaches to maximum range, which is 150,000 in this case, the PWM output is set to 1 and counter is set to 0. It start counting from 0 and continue to generate this PWM output. Let us realize this theory in programming. During programming, I'll show you some tips so that you can program better, readable, and portable. For FPGA implementation, I have 4 files. One is servo motor, which is a top module, servo motor PWM, which generates the PWM output, servo package, which includes constant values, type, functions that will be used throughout my module, and by using a package makes my module portable, and system test bench, which will be a test bench to test my module. This is the file servo motor VHDL, our top module. To increase the readability of a module, we should always present comments in it wherever it's necessary, so that somebody who takes this file can read it and understand it, what does that code means. Also, we should include a header which should have information like your name, file name, what does the file do, when it is created, and it belongs to which company. I'm using Emacs editor because I'm more confident about it. Feel free to use any other editor too. To include header, I simply call a template insert header. As you can see, In this header, I have a title where I write this top module. This is a top module, and the file name, my name as an author, company name, created on, last update, standard, and some description about this file. If there's a copyright disclaimer, please include this, and any additional information too. Next, of course, to include a standard library. This everybody knows about it, therefore it's no need to be explained. But the next step is important if we want to make our module portable. If we want to use this module in different projects, then it should have its own library which will go along with it and can help it to get integrated with other projects easily. So I have defined a library called Servo lib. By referring to this library, I can use packages in this module in different files. Of course, then we need to define the top module entity. In Emac, it's easy to define. We just have to define the standard word, and it's going to ask for the name. Let's say servo motor. It makes the work easy if we have the same name as the file name. So servo motor VHD is my file name. The entity will be also same name as servo motor. If you have a generic parameter, then defined here. If you're not, then you can skip this part and directly go to the ports, and then you can define the ports over here. So I say application clock I. So as you see, I included _I in my name of the port, which also indicate the direction of the port. So for input, I have _I. For output, I have it _O. So the direction is input, and type will be std logic. And now it's going to ask me the comment about it. So it's an application clock. And then of course application reset, which is also input direction. Make sure to use reset as active low because it saves energy. So therefore I will have an input direction std logic. It's application reset. In application reset, if I want to use active low, then I named as reset n, that is reset negative, and then _I, which says the direction. For other ports, I'm just going to copy paste so that I spend less time on coding and more time on explaining. So this is how I write entity definition. So _I used, _I, _out for out, the type comments, and also I group them into a small command like its application ports, a servo motor control signals. So it's very easy for the next developer to understand what this ports belongs to and what does that mean. Moving forward, now let's go to definition of architecture. Same as entity, we have to say architecture space. If it belongs to the same module, then I prefer to have name like servo motor arc. This is a top module, so I need to include that module which is going to generate PWM signal by taking input as a position. Over here I want to drop a suggestion that try not to include a code on the top module. Try to keep only instantiations so that the top module look more cleaner. So this is my instantiation of my another module which is going to generate a PWM. As you see, I have used a servo lib dot syntax to instantiate instead of conventional way of including components. Similarly, what I have done for the top entity, I have done same for the internal modules. I just have to press Ctrl CB so that Emac can automatically align the lines. Please notice that I'm including a lot of comments to give more information to next developer and using its own personal library. Therefore, I don't have to depend on the library of the project. This is how the top module is defined. Let's go to the module which generates the PWM signal. Again, we have to include header, description, and then of course the standard library. This module will also going to have some arithmetic equations, therefore I'm going to use numeric library. Then I'm going to include the lib, its personal lib, a private lib, or then if I have some constant defined in a package and I want to use that package in this module, then I have to include that package via its private lib. So for that, syntax is use servo lib underscore the package name and the all whatever is defined in the package, or whatever architecture you have in the package. Then the entity definition. This entity definition should be same as you instantiated in the top module. Architecture, similar name servo motor PWM underscore arc. Again, I want to stress on the point that you should make sure the naming of the module should be same as the file and indicate and include underscore I and underscore O for input output ports. Also, comments should be appropriate and should be reasonable so that people can read and understand what you have programmed. Let's go to define some signals. To define signals, we need to write signal and then name of the signal, then the type of the signal, and if there is instantiation value, and the end comment. So all signals, all ports, all instantiation should have comments. As you can see, Emac is actually asking me to put all this so that in one go I will be having the code which could be readable and very appropriate for a professional use. So this is how you write a signal in Emac, and I have defined a signal called position S for position unsigned. Similarly, I'll do the definition for other signals. As you can see, I have other signal called PWM counter, which is defined in the theory, which is going to count till 150,000. Then I have a PWM compare. This will be the signal which contains the position plus 195 value. This will be map position, which will contain the value PWM counter divide by 256, and then this will be a output. This will be a signal which is latched to the output. I define PWM counter as 18-bit because the maximum value I want to reach is 150,000, which is 18-bit value. Now if I shift this 18-bit value to the right side with 8-bit, I will be left with 10-bit. That is why PWM counter compare S is defined for 10-bit. Further, when this PWM counter compare value is compared with the position, then the comparison should be done in binary, and that should be compared with the equivalent bits. Hence, the map position S, which will be compared with PWM counter compare, is also assigned 10 bits. Then after begin, start writing a code. Very first, I like to write all the output ports which are latched to the input signals. So output ports. Therefore, immediately who's reading the code in the beginning knows which signal is actually latched to the output. Here I want to also say that for signals I use _s as suffix, and while reading the code I can immediately know this is signal, this is input port, this is output port if I use this suffix. So PWM out is actually copy value from PWM_s, and there you have. So whatever value is going to be there in PWM_s will be copied to PWM_o. The next, I would suggest you to write, if you are going to take some input ports and connect it to some signals, then you write them here. For this purpose, I'm taking position S as 7 down to 0, only 8-bit, and position I is 7 down to 0, 8-bit, which is defined 8-bit because we're going to only take position from 0 to 255. And the compare counter is basically going to take the value from the counter divided by 256. As you know, by shifting 8 bits towards the right, I can actually get the value division by 256. So I just have to take MSB of the counter. So 0 to 7 is gone, only the MSB is 8 to 17, because 0 to 7 I have shifted right, and they have gone, they are like 0 now. So if I shift all the bits towards the right, 0 to 7 bits are gone and only MSB bits are remaining. Therefore I can copy this MSB bits to PWM counter, which need to be compared. Now I will define process, which should be sequential because we're going to count a counter with respect to the clock, and clock is given is 50 Hz, and each counter will increment after every 20 nanosecond. And according to a theory which we have done before starting the coding, we have to count till 1 millisecond of time to reach 0th position, and then afterwards we have to increment the counter and compare with the position accordingly. Therefore we have to use a sequential process in this case. Combination process is also another kind of process which is being used in VHDL, but it is not synchronized to the clock. Therefore it's hard to predict the output, and also it will not be a good way to go for a counter implementation. Always label the process, loops, or case statements, so that it's very easy to go back and see what process is doing what label, if the label is present. So p underscore, I'm going to rename it to as generate p underscore generate PWM, and of course the clock is application clock, which is coming. Reset is reset node, and the description is this process generates PWM. So I have a comment on the process. I have the label for the process. I have the sensitivity list as application clock I, because it's a sequential process. As it is sequential process, I'm only going to trigger this process when I see the application clock going high, not down, going high. And if there's a reset, which is again going to be sequential reset, and reset low, active low, then only I'm going to reset this process. So this is how the definition of process is done, and then I'm going to write a code inside it. This process is going to generate PWM. Therefore, the counter should run in this process. And when the reset happens, we should reset the counter too. So for us, the PWM counter is a signal, is STD logic. Therefore, it should be set to 0 by setting all values to all bits to 0. And the signal, which is latched to the output, should also set to 0 when reset happens. Now this counter should run to the maximum value, which is 150,000. The PWM counter is unsigned, hence it could be directly compared with the numeric value. PWM counter S, if it is more than 150,000, then continue running. So PWM counter S, PWM counter S plus 1, continue incrementing. Else PWM counter S set to 0. Here additional tip: if your PWM counter is the STD logic vector, then you should convert it to unsigned for comparison and for incrementing, so the code will look different. For example, if it is STD logic vector, then PWM counter should be this, should be STD logic vector, unsigned, add, semicolon. So first you convert to unsigned, then increment it, and then convert to STD logic vector. If PWM counter you have defined as STD logic vector. If it is defined unsigned, then it is not required to do this conversion. It could be directly increment. Now on this stage, I would like to take the position value, which is defined by the user, to internal signal. But as the equation says, position value should be added to 195 as a constant. So this constant I will define in the package. The preference is to define all the constants, all the functions, all the type def, user type def in the package. Therefore, I have a file called servo underscore package. Let me define it quickly because it's not a big file and it's very easy to understand. Again, the header is there, standard library is there, And if you want to use unsigned, then numeric std is there. So package definition is done, and it's easy to have this package a code. So basically I define a constant called adc add underscore c, which is unsigned, and it has a value of 195, a constant value of 195. I have included this package in my file when I started programming this module. Therefore, I can use this add underscore c throughout my file. And this is what I'm going to do now. So I will have a signal. I will have the position plus 195 as a value copied to internal signal. So map pose will be my internal signal, and it will have a user find input plus add underscore c. Map position s is unsigned, add underscore is unsigned, but pose underscore s is std logic vector. Therefore, I need to convert it to unsigned. And then do the addition and then copy into map position s. There's a rule here which a programmer should follow. The rule says when we add two binary number, in this case the position s, which is given by the user, is 8 bits, plus add underscore c is 195 in decimal and 8 bits in binary. Then the output as we get should be 9 bits to get all the resolutions. But in VHDL, if we do this and it results in 8 bits, this leads to wrong values. The correct way of implementing in VHDL is to convert the 8 bit to 9 bits, both of them, then do the addition and then copy it to 9 bits. In our case, output will be compared, which is map underscore pose underscore s, with the PWM counter map. Therefore, both binary should be of same length. Hence, it is required to have 10 bits. Therefore, pose underscore s is defined 10 bits. Add underscore s c add underscore c is also defined 10 bits to achieve output of 10 bits of map underscore pose s. Now this can be compared with 10 bits PWM counter compare s. So this is to make easy, and this is a very common mistake a developer do, and it's very hard to find sometimes because the bit resolution losing somewhere we can only come to know after simulating the specific values or the higher MSB's values. So always try to give more efforts on bit depth while doing the arithmetic calculations. After this, we have the value from the user as a map position s. This needs to be compared with the counter value. This is done in this if statement, where I compare map position value smaller than or equal to PWM counter compare S. As both of them are unsigned, therefore I can compare directly. I use smaller and equal to because, as we had seen in the equation, they are not exactly similar, but they're equivalent. When the map position value is smaller or equal to the PWM counter compare value, then we're going to set output PWM S to 0. Else if when map PWM counter compare S reaches 0, then we're going to set it to 1. Here I did a small mistake. The mistake is that the PWM counter compare has its initial value as 0. Therefore, from the initial, the PWM-S will be always 1, which is not correct. Therefore, I set the default value for PWM counter to its maximum and allow this if statement to run when it sees the PWM counter at its maximum, which implies it will increment when it starts and then it's set to 0. Therefore, setting PWM-S to 1. Same I have to do with its initial value, that is set to all 1. Now let's write our test bench for simulating our program. Here I design a test bench, again with an header, standard libraries, the private library for the module, definition of system, test bench. As there is no ports or generic ports, therefore I don't have to define all of them. Start of architecture. I have a signal for clock, reset, position given by the user, output of my module. So the clock is basically toggled after every 10 nanosecond, which generates 50 Hz. That implies after 10 nanosecond it toggles from 0 to 1, and after next 10 seconds it will toggle from 1 to 0. After this, there is a small process which set the reset not to 1 and increment the position given to our module by the user. So this is the instantiation for our module, and all signals are connected over here. So in this test bench, when a servo motor PWM output is changes from 0 to 1, the position will increment. To save time for simulation, I'm going to change the position increment to 50 so that it's visually we can verify that our counter is able to increment and also able to generate PWM with different width. So I imported my files into a Quartus Prime project and compiled, and there is no errors. Now I will run a simulation in ModelSim. In simulation, we can see the position changing from 50 to 100, 100 to 150, then 200 to 50, and then 44. With respect to the position, PWM width also incrementing till 250 and then decreasing again. This verifies that our program is working correctly. Thank you for watching my video. Please do subscribe my channel, like the video and share the video with your friends. Do write me in the comment section what all improvement you would like to see in next video, what subjects I should take over, so that I can help you out to improve in FPGA world. Then see you later, and I wish you good luck.